Okay, we're ready to go. So lecture 2, and today we're going to talk about AI and data science. So the first sort of idea I want to share is the following thought, that there's an entire sort of spectrum of where we can go from what we might think of as classical statistics all the way to deep learning techniques. So what we see people talking about breathlessly in the media or large language models. And this is a total continuum. There's no discrete thing where one thing starts and another thing stops. It's a total continuum. So one way of thinking about what we're looking at is this, what I think of as a little formula, is that the two things we're trying to do is we're bringing together data and models through computation to make predictions. And this is what's going on right across the spectrum. What differs is the size of the data, the size and type of the model, the nature of the compute, all leading to the prediction. Our aim is that we would like to make that as part of a decision. So we've got a decision to make on the back of data. If it's data science, it's not very often a business decision about, how we should distribute our investments in products, in stock, or how we should market or advertise, whatever we want to do. If we're interested in policy, so in government work, it might be a decision about where we need to invest government time to support the innovation economy. You see a lot of data science now in economics with that purpose. So in some sense, when we think about our data and our model, this is coming from our world around us. And the model itself is some typical abstraction of the world. And in statistical modeling, that abstraction is what I think of as weakly mechanistic, like it contains some properties. So I realize I don't want this one. It contains some properties. That come from some understanding of the world, like smoothness. Like, because you're live, you would be really surprised if I were to disappear from here and reappear on the other side of the room. That's a smoothness assumption. Now, smoothness comes in practice from underlying physics at scale, right? Actually, I don't know what quantum things do, but I think they can do something like that. But then as you look at the physics and it all sort of scales up, you don't tend to see those sort of discontinuities. I mean, you do see discontinuities, there's edges to things and whatever. But a good weakly mechanistic assumption is that generally we expect things to be somewhat smooth. Of course, the level of smoothness can vary. Another common assumption is things are linear. That's often not correct, but it often makes it easier to interpret the models that we're building. But if you go all the way up to sort of modern machine learning methods, or even machine learning methods from 25 years ago, they're basically uninterpretable in the classical statistical sense. They're very complex models that, and in deep learning, we're building compositional models. And there's something about this composition, which, I don't think we have a full understanding of, that is capturing something about the nature of the world around us. So the two of them have to be composed together. And when we're doing machine learning and statistical inference, we're typically using approaches related to objective functions to make a prediction. And then that prediction feeds a decision about what to do in the world next. Sometimes, and this is what you're seeing a big debate in, when people are talking about how to improve existing models, they're talking about incorporating the prediction in that loop, incorporating actions in that loop. That's something like reinforcement learning does, and something that if you're doing if you have an action step that you're learning over, then you are actually incorporating the decision. So an end-to-end model would do that. But I'd say the majority of models don't. They just make a prediction, including large language models, which is one of the sort of criticisms of them people make. Now, at the starting point, this notion of classical statistical analysis, which is rooted in the thinking of the sort of a century ago in terms of how do we validate whether the data is telling us what we think it's taking us. It just remains more important than ever, both what we call confirmatory data analysis, so that's like answering a question, and this area known as exploratory data analysis, which is very much what we're doing to visualize our analysis bugs when we're trying to pull together the analysis. So what is machine learning? Well, I like to take this little formula and decompose it. So the data is a set of observations, and they could be either actively or passively acquired. So it might be things that we're going out in the world and acquiring on purpose, or it might be things that people have just laid down by wandering around with their mobile phone. So surveillance data, which is very common in statistics. So when we're thinking of the COVID pandemic, there were these large-scale surveillance studies where people were doing randomized controlled trials to test people in the population, whether they had the disease. It's a form of active acquisition of data. But alongside that, people were also wandering around the country with their mobile phones, commuting, laying down information about where they've traveled, which was totally passively laid down, but we could also do analysis of that form of data, combine it with where the pandemic was, and predict where the pandemic is going next. And in fact, my own experience of doing that is much more in the African context, well before the pandemic. It's a very useful approach. So the model is our assumptions, and those assumptions could be based on previous experience, such as, and this slide's very old. So when it's saying other data or transfer learning, that's what's going on in large language models and one-shot learning, right? But this has always been true. It's not a new sudden thing. It's just the scale and the size of the models which they're doing. Or beliefs about the regularities of the universe, what we might think of as so-called inductive bias. So the prediction it could be an action to be taken, but it could also be a categorization or a quality score. And that would be a typical thing that we're seeing in supervised learning scenarios. Now, there's this report that I think still is very informative, Machine Learning, Power and Promise of Computers That Learn by Example. It's a remarkably prescient report. It mostly remains true today, even though it was published in sort of 2017 from work done in 2015, 2016. In fact, I still think, because it's sort of foundational in that sense, it's often more informative about what's happening next than the sort of more recent ravings of recent carpetbaggers and shysters that have entered the field. So, because it comes from a period when it was basically people who'd worked on these things, understood how they operated. So to combine these two things, we basically need two things. One, well, and this isn't true of all algorithms. There's algorithms like k-nearest neighbors where you don't quite have this. You might have this implicitly, but you don't quite have this. But I tend to think of decomposing in general machine learning algorithms into two things. One, a prediction function. And the prediction function is like, for test data, what goes into the model to make our prediction. And the other is the objective function, which we might also call the cost function or whatever, and defines the cost of misprediction. So in some sense, it's very simple. And so how does that drive things forward? Well, machine learning's, I think, the driver of two different domains, which the first of which, data science, arises from the fact that we now capture data by happenstance, and we capture extraordinary quantities of it. The fact that the computer can absorb this data 300 million times faster. And, artificial intelligence is a terrible term because it means totally different things to different people, and it conjures up specific meanings in the general population, which are often unrelated to what the technology is. It's a marketing term, pure and simple. But if you want to sort of think about where it fits in the broad scope, I think probably emulation of human behavior is a description that captures quite well what people think of as AI. I mean, of course, at one level, people are just doing very simple algorithms like we'll see next and saying that's AI. It's part of their marketing strategy. At another level, some people are saying, no, it's generative AI. Well, generative AI, humans can't do what generative AI does. So that's not emulating human behavior. It's going beyond that in some sort of way. It's an appalling term, though. I mean, really, it does have some advantages in that it means the public are more engaged in the debate of deployment of technology than they would have been for previous waves of technological revolution, where they wouldn't have sort of perhaps had such a vested interest, because intelligence is such a personal word. Now, there's a connection between these two things that is sort of like what I think of as the Internet of Things, like in terms of not just what people sort of think of IoT, but your mobile phones and the fact that everything's all connected and laying down data. But there's something quite deep within that term that is worth highlighting. It's not an Internet of Things. It's an Internet of people. And this is where the problems start, because it's a classic engineering computer science thing to do, to abstract in such a way that means you don't have to worry about the downstream. So if you say these are things, then you don't have to worry about downstream effects, right? Actually, they're people. There's very little on the internet. I mean, even in manufacturing, which is a big area for Internet of Things, you know, the senses are somehow integrated with people and what they're doing. But in general, where people are most applying this, it's not things, it's people. And then just to highlight something, another area in which that ugly approach rises its head. This is 1981, January 28th. And this January 28th is still known as with this incorrect term, Data Protection Day, because the actual original act is Convention for Protection of Individuals with regard to automatic processing of personal data. This is the basis of data protection legislation that we now would refer to as GDPR. But look at the words. It's protection of individuals, not data. Data is not endangered. Data is growing at a larger rate than ever. And this is sort of undermining the intent of the legislation, which is, I think, solid legislation in terms of the way it's written, but being appallingly implemented by people who sort of not following the intent of the legislation, but tying everyone up in legal knots and charging large amounts to claim that they can untie the legal knots. Whereas the intent of this these series of acts, is to give you personal data rights over how you are represented in the machine, rights of deletion of your representation, rights to query decisions that are made about you according to that. So these are personal data rights legislation would be the best way to think about them. Lots of challenges in trying to sort of improve the way that they're implemented. But one of the most important things in reflecting our individual dignity and our aspirations as humans, not things. So what does machine learning do? Well, machine learning automates through data. So it's very strongly related to statistics, and it's underpinning this revolution in data science. And with AI, of course, we've got all these things like logic, robotics, computer vision, language, and speech. But with data science, it overlaps with databases, the historical field of data mining, statistics, visualization, and software systems. So with this, you're sort of covering the whole spectrum of computer science when you start thinking about machine learning, AI, and data science. And it's sort of a bit, as you look in this department now and you look at the part 2 projects, I mean, it's sort of weirdly rare to see one that doesn't involve machine learning in some way, but, and weirdly rare to see one that doesn't involve neural networks in some way. Now, this is an utter contrast to where we were 10 years ago, where it was only the machine learning group that was offering such projects in computer science departments, or perhaps, the computer vision, language, and speech groups, maybe robotics. So how has it become so successful? Because it's codifying processes that we can now automate, and it's codifying them just through observing data. And often that data is coming from people. And the codification is extraordinary. All that large language models are doing is codifying the process of constructing language just through data, rather than from first principles, just seeing a large amount of data at scale. But when you're building systems from this, it often involves interconnected components. Even a large language model itself is going to connect to something else in order to deploy in some interesting way. And that tends to mean that there's interconnected components. And then there's questions of compatibility between components, APIs, these types of calls. And all of that comes into the data science. Now, if we look at the history, you can compare this to the history of production. So actually, probably another example I should put in there is things like the Whitworth thread. So the Whitworth thread was the first standardization of screw and nut and bolt threads. So until then, you had to make your own thread for each nut and each bolt. So, every manufacturer would cut their own, right? Until that's standardized. And imagine what that was like. So, it's an enormous transformation to standardize threads. And of course, we still have imperial Whitworth threads and versus metric, M6, M10, whatever else threads. But there's at least a couple of standards that we can now use that if you buy a wing nut from one source and a bolt from another, as I did on Saturday, that they will screw together as long as they're both M6 or M10. And just imagine a world where that wasn't possible. That's the kind of world we're in machine learning at the moment. And part of the problem is we don't even know what threads look like. We don't even know what the interfaces should, how they should standardize, because the technology changes. Just as we think, oh, it's a REST API, then we're all like, oh no, the REST API isn't sufficient, or it needs to be a Docker container or whatever else. These interfaces are moving, which is a sort of interesting challenge. So how does machine learning work? Well, you know, I'm sure you've seen it before, but just to sort of review the type of thing that we're doing is, I might be trying to predict for Amazon whether someone's going to purchase a jumper. And I can do it with something very simple called logistic regression. So this is the classic way that the statisticians think of logistic regression, that they actually say that what's going on is that there's a certain odds, which is the ratio of the probability of buying to the probability of not buying. And then you predict the logarithm of those odds, because this is a positive number. So it's a positive number, which is sort of less than 1 if the probability of not buying is greater than the probability of buying, and greater than 1 if the probability of buying is greater than the probability of not buying. So if we take the logarithm of that, that logarithm takes the 0 to infinity and maps it across the real line, and the piece that was mapped between 0 and 1 is mapped into the negative half space. So what you end up when you take log odds like this and some sort of weighting of some features you might think are interesting. So look, as I get older, I wear a thicker sweater, you know, but I don't buy them. I just get given them at conferences from places like Cyber Valley for free. This is a nice thick one. And then I just wear those. But also because I live in the north, I'm more likely to buy a sweater, right? So there's some sort of weighting of the latitude where someone's living, and their age might be telling us what's the probability they're looking to buy a sweater. And then there's some sort of parameter that sets the base level. So if it's probably with any purchasing, it's very unlikely anyone ever buys anything. So W0 would be very negative, so that, you know, ignoring the influence of age and latitude, then the probability of buying a sweater is low. And then you would probably have a positive weight for age, which would mean the older you are, the more likely to buy it, and a positive weight for latitude, which means the sort of further north you are, the more likely you are to buy it as well. Of course, that's going to raise a problem. Now, this is known as a link function in statistics. So this relationship where we're going from something that's linear and looks very interpretable to something that, as we'll see in a moment, is nonlinear. Because actually, if we go along this input axis here, and I'm now thinking of F as being the combination of W0 plus W1 age plus W2 latitude, then what we see, the output probability of buying, which we can calculate, is now this logistic function, which is very widely used in machine learning. But you very rarely see it described in the way I described it in machine learning, because that's the statistics motivation. It's sometimes called the logit. It's called the logit functions in statistics very often. And the logistic function is actually coming from us corrupting the fact that the logic function leads to logistic regression. Ironically, in statistics, before they did logistic regression, they did probistic regression, which was the probit function, which is a different function, which we don't use so much nowadays. So what we end up with is, in machine learning, something that looks a bit like this. The probability of buying a sweater is the sigmoid of that linear set of inputs. Or we would often write it, Carl-Henrik and I, something like this, where there's an inner product. So actually, what we're starting to do is hide what these features represent in some sense. They just become a feature vector. And this is a sort of fundamental approach that is determining, or in combination with other feature selection approaches, determining probably what Google videos you get shown on YouTube, or what, I don't know, who knows what TikTok's doing, something addictive. But, you know, underlying a lot of those algorithms are these very simple machine learning algorithms that also are statistical algorithms. So what that is just this prediction function. Some output we're interested in, probability of buying, is some function of the input and some set of parameters. Now, in the world of deep neural networks, this is a lot more complicated. We just start composing these functions together to create something more complicated, but the basic idea is the same. So the objective function, well, that's what allows us to do the fit. So the classic objective function, which we wouldn't use, well, you know, there's some interesting reasons why it could be used. It's known as a Breyer score in classification, in statistics. And the Breyer score is interesting in itself. But typically, you would use a least squares objective function, where you're looking at the square difference between the target and the output of your prediction function and summing across the data in a regression setting. And that turns out to have all sorts of interesting probabilistic interpretations. So those are the sort of two components in a model, and they'll vary different model to model. And here's the key slide in terms of the difference between statistics and machine learning. What's the difference between these two equations? Anyone spot it? What's the difference? Say again? The letters, yeah, just the letters. And it's traditional in statistics to use beta for regression weights. And it's traditional in machine learning to use W. Where does W come from in machine learning? You know, I just said it, but actually it's in machine learning, it's not so much regression weights, but what type of weights? Synaptic weights in neurons. So the W is for weights. So we came along and started naming everything with W, but before that, statisticians had used beta to represent these coefficients. But I think this is a really nice separation, because statisticians, when they build these type of models, they're typically less interested in the prediction and much more interested in the interpretation. So the sort of thing a statistician would be interested in is, you know, understanding what the relationship between age and sweater buying is, and whether age has a high effect. And if I can decompose on the log odds a percentage of contribution of what is coming from age and what is coming from other things I might be interested in, sort of, for example, like indexes of deprivation. These are scores that you can find locally that show that, or that summarize the level of deprivation in a very coarse way. And you might be interested in trying to predict, instead of this, you might be interested in predicting lung cancer. And you might be interested in looking at whether people smoked, whether they drank, whether they came from a deprived area. And these coefficients become very important. In fact, when you get to, I'm going to struggle to remember the name of the Q-risk. Yes. If you look up something called Q-risk, so when you get to something like your late 40s and 50s, they start testing your cholesterol. And on the basis of a cholesterol test, they decide whether or not to prescribe you statins. And the Q-risk score, as far as I understand it, is just a logistic regression that is combining all these questions they ask you about: do you smoke? How much do you drink? All these sort of things like that. Then they use that to give a probability of you're going to have sort of heart disease. And it does include a cholesterol measurement, but they also sometimes will compute the score without that cholesterol measurement. So some examples of, you know, I like my Uganda examples, some examples of working this in practice. So this is work that was done with my PhD student at the time. This is a number of years ago, 15 maybe? No, less. 11 to 8 years ago. Ricardo Andrade Pacheco, John Quinn, and Martin Mubagizi, who was at Makerere University with John, and more recently has been at UN Global Pulse. So there's, well, let's just pull this. Does that still exist? Oh, no, there we go. Error to call that up. Oh. So they've changed their website. I'm going to have to fix that link. But they've got this AI development group that also led to this work, which is very cool. So I'm going to show you some other case stuff for this, but this is what Ricardo did with UN Global Pulse after he'd left Sheffield. And it turned out we were working on malaria prediction in Uganda, and we were trying to, they have these district level data about how much disease there is in each different state. And you can see it's at the district level. We wanted to find a grain level, and we were trying to combine it with satellite information about vegetation, rainfall, these other things to try and fix these measures, because these are reports from health centers that don't actually have rigorous testing capability for malaria. So malaria is commonly confounded with typhoid because it exhibits in the same way in terms of fever, but it's very different in terms of its treatment. And the only sort of rigorous test is to actually look under a microscope and see if you can see the plasmoid, this sort of single cell entity that causes the disease. So we were really interested in trying to help with this. And that's what Ricardo's PhD thesis was on. But we just had a series of negative results. So this is just moving forward, looking at malaria levels across the country. We couldn't get anything to work. And the end of Ricardo's PhD thesis was kind of failure. It was disappointing, but we just went too complex with this stuff. Our models, our ideas didn't work. Then Ricardo went to UN Global Pulse. And actually, the way this data is gathered is through something called HMIS, which is a sort of program, a very advanced program, far more advanced in Africa than it is here. It was shocking how bad we were here compared to how good they were there at the beginning of the COVID pandemic when I was working in that space. But HMIS collates data from health centers. And as academics, we only got access to the collated data. But when Ricardo went and worked with UN Global Pulse for a couple of months and looked at the underlying data, he found that some health centers don't report in a given month. And there's missing data. And so what do they do to deal with the missing data? They just effectively assumed it's zero and average, yeah. Classic type of thing that can happen in a data science pipeline. This destroys any spatial characteristics in the data, basically. The same thing happened, you can look it up, with Ebola, when lots of foreign academics came in to try and study Ebola in, I guess, Liberia and Sierra Leone. Because, you know, this is one thing, people get super interested in African diseases when the diseases seem like they might be able to escape the continent and affect you. Only about 20,000 people, I think, died from Ebola, which is a lot. It's a terrible thing. But, you know, the beautiful thing about it was they put an enormous investment to give Sierra Leone and Liberia quality of health systems that are up to stand with Uganda's. The Uganda Minister of Health actually went to those countries. There was a video somewhere of her talking about how shocking the information systems were. So Uganda has it pretty good, but we were getting this collated data. So what did Ricardo end up doing after his very complex PhD thesis? Well, he ended up just filling in those missing values by interpolating over time using Gaussian processes. And what you see is the result of that interpolation. And what this means is that you can look at typhoid, you can look at malaria, and you can look at it in a way that made sense. Up until this point, it never made sense. And this was used in, I think it was a cholera outbreak in Kampala. Kampala is the one down here. Is that Kampala? Kampala, it's around here, Kampala. I'm guessing it's there because it's a small, Kampala district, which is the capital. And there was a big outbreak in Kampala, and they combined this information that Ricardo had been working with information from telecoms about how people move between towers. So just live information of tower to tower movement, totally anonymized, and just with these little arrows, just going. So you could look at this map and you could see where the disease was and where people traveled, with a map of roads sitting underneath it. And then they were using that to directly decide where to put resource in order to stop the outbreak. Really beautiful. And they set that up, you know, my friend John and Martin, they did that in, you know, a matter of a couple of weeks. You can see, I mean, it's such an amazing place to work. So we were then sort of trying to sort of combine this with this other information about population density. There's all sorts of extra information that you can use and try and combine with this to try and improve the extra data. And this one, is this the, okay, here's, I think this is the typhoid, so it was typhoid. National Task Force supporting response to disease outbreak in early 2015, series of interactive data visualizations, data collection, data cleaning, combining data sets, quick insight, visualization. It's such a cool project. You know, this makes such a difference to people, and it's simple to do with the right people and the right data. You know, very few people involved on top of the underlying infrastructure, which of course is critical that they have this. And we did not have this in the UK for COVID. We just did not. That's why it was such a mess. for the first 8 weeks. No capability. I mean, you argue why we don't have it. Well, because we don't have ongoing pandemics here, whereas, you know, you can do in Kampala. I mean, if you want to, if you look at Ebola is very common in this region here. So the capabilities of disease monitoring in Uganda are extremely good. There's the Uganda Viral Research Institute. Very, very cool stuff, led by these people. And then actually, so here's some Corsa maps describing the same work. This was the first Gaussian process school we did, Makerere 2013. That's Ricardo, that's me, that's John, that's Martin. And these other attendees, some of them from the Uganda, this guy I think is from the Uganda Viral Research Institute. This is Joyce, whose other work you heard about more recently. You know, it's actually so cool to see this picture because I'm just looking at every one of these people is now leading groups, doing big things, attending Data Science Africa in its latest form. But the very cool thing that I like that Ricardo then did sort of at the end, and we didn't really quite publish this, but and you could definitely get a better visualization. I just cut this out of a GIF that he sent me, is he looked at the trend of disease over time, and then he decomposed it with a Gaussian process into two trend terms. One, the long-term trend, which is the red, and the other one, the shorter-term trend. And then what he's looking at, and in here, is looking at the shorter-term trend and then trying to color what's going on. So down the bottom left, there's two axes, the rate of change, so the gradient of the blue curve, and on the x-axis, whether you're above or below the red curve, right? So if you're down here, you're below the average, the long-term average, and you're decreasing. If you're here, you're below the average, but you're expanding. If you're here, you're above average and expanding. And here, you're above average, but decreasing. And then we have some gray area. Now, you could argue whether that should be a circle or not, but Ricardo happened to do this square, which would be like a L1 norm on that. Maybe that should be a circle, which would be like an L2. That's not L1, is it? No, it's like an L infinity norm on it, isn't it? Yeah. And then so you can show the map. And then you can actually look at directly at what's going on in the different areas, whether they're above trend or below trend, whether things are getting worse and things like this. So just a different form of visualization. It's not, in some sense, it's not technically difficult. It's just a very cool idea Ricardo had, I think, taken from the economics literature for this sort of form of visualization. So where does deep learning come in? Well, the things we've been talking about so far is very interpretable models. So we can actually go back and sort of answer questions from the Ministry of Health about the parameters as long as we built the model well. But a lot of modern machine learning methods are less interpretable. So this is going back to 2014 when this sort of revolution in learning sort of took place. What we start doing is convolving these things together. Now, it's not that complicated to imagine. All you're doing is feeding the output of one of these models into the input of another, right? It's just mathematical composition. And the reason you can do it is, of course, because we can compute gradients going back, so-called back propagation, to understand when we have errors in the objective function, how the gradient propagates back here. And many of the technical challenges were actually that you tend to get problems as you go back through the model that the gradients disappear. And so you get a zero gradient here. So people worked a lot on engineering things to do that. That's mostly the advances we made. Big advances in computation, big advances in data availability, and then lots of tinkering around to try and deal with these practical problems. The one of gradient vanishing, eventually, I mean, the main way is using these rectified linear units. These layers here are actually the fully connected layers. These layers are convolutional layers. And deep face was the first face to be superhuman on this data set. All just seems very natural that we can do that now in terms of face recognition. But it was mind-blowing in 2014, just as mind-blowing as large language models are now. But now just as accepted, just as large language models will be. So what do I think is going on? Well, I like to think of it as this sort of pin structure. It's very simple. This is a one-dimensional deep model. These are my parameters. Each function has a one-dimensional input and a one-dimensional output between each layer. And if I'm trying to classify something in this model, it falls through the model according to where the parameters are, which the parameters in this case could be like the pinpoint on the ReLU or the inflection point on a sigmoid, depending on what basis function you're using. So at the moment, this model is not classifying correctly because it's just at initialization. So it makes some errors. We use the objective function to modify parameters, and the parameters all move around, in this case in one-dimensional space, but in a deep neural network, in a hyperspace, millions of parameters, thousands of at each level, you know, potentially thousands of dimensions. So you're sort of playing this game of pinball in this massive hyperspace. So once you move the parameters in the right way, then things fall through the model. And this is like, you know, this is at the bottom here is the one-dimensional output to my logistic, right? Does that make sense? That's my intuition. This is how I explain it. I say it is not hard to understand. Right? This is not, oh my goodness, we can't understand what's going on. We built these things, right? You know, yes, interesting things happen with large data, unexpected things happen, but it's not hard for regular people to understand what's going on. It's hard to imagine it going on in high dimensions. And one of the effects in high dimensions is these spaces get so massive that, you know, for example, no ball went here. So we don't know anything about the quality of the parameters in this space because none of the data ever landed there. And that's the sort of challenge we get in deep neural networks, that you end up with portions of the model where no data ever falls through. And those parameters are just as they were at the beginning. And the predictions of the model in those regions are very, very poor. Or adversarial learning. In adversarial learning, you just go around making small changes to where these things are that are calculated to sort of upset the model and make it do stupid things. And the reason you can do that is because in high dimensions, you've got so many small changes you can make that really upset the model. So these sort of adversarial approaches. And this is, you know, this is also the source of why AlphaFold lost a game, because the Lee Sedol managed to play AlphaFold into a region the model had never seen data before. So it just made stupid decisions. So that's one of the challenges we face with these models is we don't know when they're making stupid decisions. Oh, why have I lost it over here? It's interesting. Okay. Okay, so what are large language models? Well, I think that they're really exciting because the sort of thing we're trying to teach you in this course is this relationship with the human and the computer, where the computer understands things in terms of regressions and error bars, the sort of fits that we might do with a model. The human, we're trying to teach you to understand that. But most humans don't have a very good sense of an error bar. P-values, these type of things, they're not very intuitive. People make errors with them all the time. And I think we're at this incredibly exciting point in data science when all of a sudden you could actually just make this about language. It's got incredible dangers associated with it, but it's incredibly exciting as well. So there's a lot of evidence that probabilities aren't interpretable by normal humans. So if you try and work with doctors or any sort of expert that isn't quantitatively trained, you can be very misleading. I mean, so examples, I mean, there's, I don't know how, my Twitter feed is totally filled with things on the Lucy Letby case. Now, I haven't looked into the details, but I know Richard Gill, who's the main statistician who's pushing back against that case. And I know him because in 2000, when we did, Carl-Henrik, when was AI Stats in Sardinia? And do you remember Richard Gill's lecture? Yeah, so Richard Gill then was a statistician, he's in Netherlands, and he was working on a case of a case of a nurse who had been convicted for similar things to Lucy Letby. And what he was looking at was the challenge around how they described when this nurse was on and off duty. And basically the fact that they knew what they decided which babies were murdered, and they chose which babies were murdered according to when the nurse was on duty, which is, and I haven't looked at the details, which is what these statisticians are saying has happened in the Letby case, right? Now, the reason this sort of happens is because the people who are gathering the evidence in some sense, they're not trying to be evil, they're not trying to set people up, but they can make errors of design around things like probability. And juries are well known for sort of making mistakes. There's something called the prosecutor's fallacy. So I think there's a really interesting opportunity to bring in these large language models. And sort of what we've discussed before is these models, they're giving us what we think of as an analogous state So this is the Moniac. Has anyone ever heard of the Moniac? No? So the Moniac was an analog computer that was designed for economists to model the British economy. And I think this tank is the Treasury tank. And this, I don't know what the different tanks are. But the basic idea is that money flows around this system through these pipes, through opening and closing valves. And then floats give this output here. So here's the output of the computer. And the reason this works is because money flowing is analogous to water flowing. So that's why it's called an analog computer. How many people knew that before? That it's computing by analogy. Anyone know that? So when we say analog to digital world, we use this word all the time. No one even knows where it comes from. It comes from analogy. That the machines, the analog machines that computed in this continuous way, have an analogy at the heart. This analogy being between water and money. Now, at the heart of a digital computer, there's an analogy, which is that an electrical voltage represents a 1 and a 0, and therefore I can do logic. So it's right deep in there. There's an analogy that means the digital computer does logic. It's an analog computer right at its heart. But then once you've got logic, you just build everything out of the maths on top of it, right? So there is an analogy, a physical analogy between electrical voltages and the abstract notion of logic that enables digital computers to work. But once we've got that analogy, we talk about them as being digital because they're representing numbers in a in a discrete way, digits as in our fingers, right? So what's going on with these large language models was, as I've sort of described before, this is a revolution. We have this human analog machine plugging into the digital world and being able to provide us with an analogy of what a human might have said. But just like that water, that is not actually the British economy. Well, it probably is the current British economy, but it wasn't the British economy in the 1940s. Yeah, it's sort of like someone else has got all the water. Yeah. But what's nice about it is you can quickly simulate things in it. So to the extent it's useful for simulating, it ends up giving you something that you can do what we might think of as a counterfactual simulation. What if I were to do this? You don't have to test it on the real economy. You can test it on this thing. And of course, these human analog machines are similar. So in practice, there's all sorts of crazy things that LLMs are being used for. My favorite examples are in like robot planning. And the really interesting thing is that the sort of ambiguities that we lose between the machine and the human are reduced because this machine has had large-scale access to human cultural understanding. But that's a double-edged sword. Okay, so final sort of 5 minutes just to sort of highlight something that comes up in this space, though. So who's seen this before? What I want you to do is count the number of times the people in white pass the basketball between them. And it's quite difficult because the people in black are going to be passing a basketball. You're going to ignore that and just count the ones in white. How many passes? Okay, and if you know the answer, don't tell the answer. Just everyone focus really on counting. Oh, I get a bloody advert sponsored. Normally you get away without this when you're in bed. So it's a test of selective attention. So focus very hard. Count how many times the players wearing white pass the basketball. Okay, how many passes did you count? Right. How many passes? 15? Lower, higher? 15? Okay, I think the correct answer is 14. 15, oh no, there we go, well done, yeah. But did you see the gorilla? Some people did because they smirked, and it's a kind of quite well-known test. But if you've seen it for the first time and you were following instructions, I think something like 70% of people miss the gorilla. And this is selective attention because it comes about if I tell you work really, really hard on this difficult problem, focus hard, 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 then you tend to remove your broader context, your ability to see the larger picture. You tend to sort of somehow attentively focus in with your narrow bandwidth, and you miss big things. This is the life of the data scientist because you're constantly working on these really, really hard technical problems, right? And then also when you go and present to your boss and say, this is really, really technical and hard, you're going to have to pay attention, they also miss the big picture. So this is a major problem in the space of data science. I call it data selective attention bias. And there's this great example that you'll see if there's some notes that you can play with, and they'll give you an example of it in practice if you play with the notes from this lecture, but it's not officially part of the course. It's just something for you to see. When someone seeks, said Siddhartha, then it easily happens that eyes see only the thing that he or she seeks, and he or she is able to find nothing to take in nothing. Seeking means having a goal, but finding means being free, being open, having no goal. Now, both modes are part of our lives, right? If we're coding, if you're looking for a bug and go, no, I'm going to be free and open and have no goal, and the bug will come to me, it won't. Well, actually it might in your sleep. That's weird, isn't it? But only after you've spent ages sort of really drilling down. In fact, I think what's going on when you find the bug like next day immediately, it's because you've put all this effort into it, but you're a little bit too narrow. And then you go away, your mind opens up a little bit. You see something that you didn't see before. So it's such a weird and interesting way that we go through these. And some people are really good at the focus, really poor at the broader thing. Some people are very good at broad, very poor at focus. So that's a sort of problem that comes up. And it comes up, now this is a quote from a book that a chapter that I wrote in a book that I edited. This problem, which comes first, the hypothesis or the observation, is soluble, as is the problem which comes first, the hen or the egg. The reply to the latter is an earlier kind of egg, to the former, an earlier kind of hypothesis. The point here is that all our observations must be couched in a frame of expectations, right? And if the frame of expectations is wrong, we get the wrong conclusions. And that happens both within our minds and within the models we're using. And this is the type of way that these things go wrong. A great example of it is, people know who this is, I hope. Who's this? Should be like a hero. He was described as a national treasure in his recent book cover. David Spiegelhalter, thank you. So this is an art, so I don't have the sound at the moment. It doesn't really matter. This is Andrew Marr talking about COVID, and then David Spiegelhalter, you can watch in your own time if you're keen, talking about what he calls number theater. People standing up and sort of saying, look at this graph, and basically none of it actually is telling you what's going on. They're just confusing you with statistics. And David's talking about that was in one of the government's presentations where they were presenting the graphs incorrectly or misrepresenting. This is his most critical interview. He was talking about their use of number theater. Obviously, he's at home because it's the pandemic. And he's great on this stuff. And I think if you do have time I think of it as data theater. He calls about number theater. I think of it as data theater. If you do want to think more about these problems and the sort of ways that come up, this is an absolutely fantastic book from David on the art of statistics, which I don't know how one teaches the sort of sense of data that is so critical to being a good data scientist, the skepticism you need, the sort of avoiding that temptation to sort of believe that because these things are overlapping, there's something funny happening with this red one, rather than, oh, it's actually just a linear decision and there's data overlap. This type of instinct David has in abundance after a career as a statistician. And this book talks about that, talks about various things around classical statistics, and also talks about, I think I don't know a better recommendation to try and gain this sense of data without just playing with data a lot, right? Which is how people get it in practice. And the problem with that is the way you get it is by making a lot of errors, and those errors can have consequences, including innocent people going to prison, or potentially guilty people not going to prison. He also has a book just out that I've only read the first chapter of, but it's just as engaging, but quite long. It's 500 pages. I think The Art of Statistics is much shorter. Just about the philosophy of uncertainty in general, which is just another brilliant read. So that's it. I think we've got a couple of minutes if people have questions. I think the one question might be that I'm going to guess you have is about the lab class, because I think it's not quite up yet, but we're going to put it up in a moment. So this is the practical, and then the lab class is going to be up by 5 o'clock today. So this is the practical, which you can do on Google Colab. Although irritatingly now, it gives you AI assistance, doesn't it? So probably can just answer the whole practical for you. But of course, if you do that, it's a bit like following GPS. And who's only ever come to the computer lab walking by following GPS? It'd be just great if someone didn't know the way from their college to the lab, which is basically what happens if you just keep following AI stuff. You have to make your own errors in order to learn stuff. It's sort of the sort of thing people study in psychology, right? But it's a sort of, this is the review and refresher that you should really have got on top of by now. But the first lab class will be here at 5 o'clock today. We were just ironing out because we modified it quite a lot, a couple of errors on it. So it would be there. Any questions? I think it says the timings of how things happen in the back to overview. In the first lecture, you've got the timing in this table about when things need to be handed in to Moodle, right? So it's into Moodle at 12 o'clock, and then we see it at 3 o'clock. And the reason we have to do that is because we don't have the hand-ins. I don't know. What was it? We didn't used to do that, but we have to do that now, don't we? Because it's part of process. Exactly. It's process. Yes, it means that you have to get that in by 12. And then that's the lab date, and we come around while you do the next lab, sort of having a ticking off that you've done it as well, and answering any questions you have about what's in it. Because these are, I can't remember, are we allowed to call them ticks? No. Oh, they're checks. Sorry, they're checks. They're not ticks. They're very specifically not chicks. Yeah. Ticks. They're chicks. Yeah. Here we go. Look. They're allowed to be checks, aren't they?
Yeah, they're allowed to be checks.
Which is American for tick. It's something to do with the
It's a unit of assessment we need to be able to somehow, we want them to be like this, but you're not supposed to according to the unit of assessment.
Because trying to get you, we're trying to, I mean, what we're trying to do with it, we're not trying to make your lives miserable. I mean, we might be doing it, but we're not doing it on purpose. What we're trying to do with this is make sure, because we know how hard it is to stay on top of different courseworks and track things